resume the record. And Rob, is it okay to record this?
Yes, go ahead.
Okay. And are you okay to upload to YouTube as well, or?
Yes, that'd be interesting. I haven't done that. Haven't had that done before. So
Okay.
yes, I'll be intrigued to see how it turns
And I'll
out.
send you the link. It's on our YouTube channel for our site, but I'll send that to you afterwards. But anyway, I'll turn this over to Rob.
Okay, thanks, Shane. Let's see. Hopefully, you are now seeing the title slide. Please say yes, Rob.
Yes, Rob.
Yes, Rob.
Okay, that's good then. So this evening, I want to talk to you about M42, or the Great Orion Nebula. And first things first, I guess, well, what's in a name? So it's got various catalogue names. So M42, or the Orion Nebula, or the Great Orion Nebula. It's also NGC 1976. And in the radio catalogues, it's 3C145, all of the same thing. And it's in the constellation of Orion, which we know. So we've got Betelgeuse up here, Rigel down here, here's the belt, and Theta Orionis, the star here in Bayer's Atlas from 1661. That's where we're going to take our attention tonight. So what I want to do is I'm going to give you a sort of short history of observations of M42. You'll see what I mean when I get into it. There's a middle section where I'm going to we talk a little bit about observing M42, particularly visually, which is what I'm interested in, and really stressing the sorts of things that you can do. What could we do with amateur equipment? Basically, that's fun. And then the final section will be a little bit more scientific and look at interpreting M42 and try and answer the question, well, what is that blobby thing out there? So we start way back when. There are no telescopes, so we've only got the naked eye. And in Western and Arabic culture, you find the star Theta, the Biacord Theta Orionis. So it's mentioned as a star. Ptolemy had it in 130, current era. Tycho Brahe, he also noted it in his star catalogues in the 16th century, and of course, as we've seen, Bayer. The one that's a bit surprising is Al-Sufi from the year 950, and I pick him out because he's usually pointed out as being the first person to have mentioned the Andromeda Nebula, but he certainly didn't see anything, or didn't report anything, at least, around the vicinity of Theta Orionis. But if we go around the world, and let's start with Australia, and they have a constellation. I think it's probably pronounced Djulpan, the canoe, and one of the indigenous peoples there in the Northern Territory had a story about three brothers of a clan called the Kingfish clan who went fishing. And they went fishing in their canoe. And then you can see the belt stars of the three brothers. But all they could catch were kingfish. And because they were the Kingfish clan, eating kingfish was taboo. And so they had to throw them back into the water. But eventually, one of the brothers just got so hungry that he decided to break the law. And he caught and ate a kingfish. And then the Sun Woman saw what he'd done and was so angry because he had broken the taboo, that she created a water spout that lifted him and his brothers right up into the sky, where you can still see them, complete with their canoe. And you've also got the fish trailing in the water behind, which is the sword. So here's the nebula, here's Betelgeuse, and here's Rigel. Notice it's upside down because we're in Australia. We're talking about Australia. Another part of the world, Central America. And here the Mayans may have actually seen with the naked eye the nebula itself, because they have a creation myth called the three Hearthstones. And here are the three Hearthstones. So we've got Alnitak, Rigel. If I remember rightly, this one is safe. Somebody, no doubt, I'll get corrected later if I've got it the wrong way around. And in the myth, the nebula is the smudge of glowing fire representing the embers of fiery creation. So it's not exactly hard evidence, but it's certainly circumstantial evidence that in a dark enough sky with the naked eye, sharp enough naked eyes, maybe you can see that the star in the sword is actually fuzzy. Let's go to Japan. And we've got another legend here. And in this legend, two sisters were walking down a road with the younger following her older sister and carrying a tub of water. But they were chased by a monster, and finding a rope, they climbed up into the heavens. And although they chased the ogre, the younger sister had her foot bitten off. And so these days, what we see is her bamboo pole with her water carrier, so the three belt stars, and peeping through a kimono.
Of a nation that stands together, glorious by your side.
And peeping through a kimono, her remaining foot, including N42. Okay. Sounds all a bit cruel, but there we go. But the story was held to represent Japanese values in terms of filial duty, strength and courage, and the will to go on to a brighter future. So there's a few versions of Orion and the nebula from around the world. We have to wait until the 17th century before we get telescopic observations. And Galileo did look at that part of the sky in 1610, but he didn't notice the surrounding nebula. And if you think about his field of view and the nature of his optics, it's perhaps not too surprising he was able to pick out the star, and as far as I know, he only saw it as a star, but there was not enough field, not enough contrast to notice anything else. So the first person to actually identify M42 as a nebula was the Frenchman Nicolas Claude de Peiresc, and he observed it with a refractor in November, the end of November, 1610. So these were just verbal records that in Galileo's case, he saw a star. In Peiresk's case, that he saw something fuzzy. First recorded images are, of course, sketches, and we have Christian Huygens, who discovered the rings or determined that the Saturn had rings and discovered Titan, and he thought he'd discovered the nebula. So he wasn't aware that Peiresc had already seen it, and he sketched it in 1659. And in many accounts, you'll find this represented as being the first drawing of the Orion Nebula. But in fact, there is one that's a little bit earlier, 1654, from Giovanni Herdiana. And he was observing from Sicily, and you can see his sketch at the bottom there. And what he's written on that is Luminosa Ensis Orionis, meaning Orion's sword of light. And in a surprisingly modern recording style, the occid bit at the bottom is occidentalis, meaning to the west. So he's told us what the orientation of his image is. Now, interestingly, you can see in Huygens' image 3 stars in the middle there, which is almost certainly Theta 2 Orionis, the trapezium, and 3 stars towards the right there, and that long gap, dark gap, which anybody who's familiar with looking at the M42 with the telescope will be familiar with. So we know for a fact from that image that Huygens has definitely observed M42. A little bit more difficult with Herdiana's. He's probably showing Theta Orionis 2, and these ones are probably Theta Orionis 1 and Theta Orionis 2 A and B. Not necessarily the brightest trapezium stars, but analysis in 1985 suggested that they better match the locations that he's recorded. It's doubtful that he really so he probably couldn't with his telescope actually resolve Theta 1 Orionis in the middle here, the trapezium. Let's jump forward to Charles Messier, who of course is responsible for us all calling this nebula M42. And this is his drawing from 1771. So this is around the time he was busily compiling his catalogue of what we now call the Messier objects. And he's got nebulas to Orion Nebula. Its date of, that date's wrong because he's actually written 1774 there. I haven't noticed that. You always find something new when you're looking at these old images. Presented to the king before the French Revolution, this was. And here we have quite clearly the trapezium. Here's Theta 2. You can see this fish's mouth region, and you can even see these angles aiming off. It's really quite a good drawing. Let's move forwards a bit. So around about the same time, top left, we have a sketch in his notebook by William Herschel. And again, you can see the fish's mouth region. Here's Theta 1, a bit of Theta 2 over here. You can see the loop angling away. Here's M43. And William Herschel examined the nebula over a number of years, and he thought he could see it changing with time. And along with, I think it was NGC 1510 Planetary Nebula, this object was one where he reasoned that unlike most of the others, remembering these were mostly galaxies or star clusters, he decided this could not possibly be an extremely cluster of stars, but must instead be composed of a luminous fluid or nebulosity. To the top right, we've got his son's work, John Herschel, from the 1830s. You can clearly see the trapezium here, theta 2 over here. Here's the fish's mouth region, and some people do see bars here, and John Herschel clearly has. Lord Rosse in the 1840s, this was his attempt. I think my personal impression of that would be that he's tried too hard. But Bond in the 1860s has produced this really quite compelling image. Remembering these are all pencils, pencil and paper in one form or another. Probably the sort of swan song of the drawing was this one by William Lassell, probably, I guess, from Malta, with his, I think he had a 48-inch reflector from 1854. This is engraved by a famous engraver, Bezier, based on Lassalle's original drawing. And you can see the cluster around Theta 1 Orionis here, and quite a lot of detail. But at this point, new technology came, photography. And the earliest one I am aware of is the effort on the left by Henry Draper in 1880. And in terms of fuzziness, that's probably started, close to Hodierna's attempts. But 2 years later, in the middle, we've got something that's, whilst it's still pretty murky and fuzzy, is starting to match the sort of detail that Huygens had managed. But just a year later, look what Common had managed, and certainly if I was ever to attempt an image, I'd be quite happy with that one. We've got M43, of course. Here's the fish's mouth region, theta, but the stars are lost because, of course, they're overexposed because this is a long exposure. And then gradually, images improved. I perhaps should have looked for and put in, if I'd found one, an image by Barnard, but I brought us straight up to date. So here's from the APOD site, which I'm sure you all know, an image dated 2017. And there's incredible detail. And I think we're all aware that there's now also incredible debate as to who's overpushed their images and things like that. And some of these really deep ones, I do wonder whether they're accurate. Not accurate. They are, of course, accurate, but whether they're really giving the right impression of what is there. As a visual astronomer, I am a little bit skeptic, as you will have gathered from my comments. And I'm sure we'll debate that at the end. let's think about actually observing M42 today. And really what I'm going to do is suggest some challenges to you, I guess. Naked eye, can you see Theta 1 Orionis? Most people can. Much sharper test is whether or not we can see any fuzziness at really, really dark sites. I suspect probably not with UK skies. Might be possible in Southern Africa, parts of the US, and Chile. I think you're looking for some. The other thing to ask is how many stars are visible within the constellation figure. So if I just flip to the next slide briefly, so bounded. Oh, I did get it wrong. It's safe down the bottom there. Between these stars and the pinch in the middle, there's a regular annual survey. How many stars can you count in here? As a gauge of how dark the sky is in your area. Binoculars, pretty much any binoculars, or for that matter, finder telescopes, but certainly from 8x30s upwards will clearly show there's nebulosity there. And of course, with telescopes, we've got the options of going visually or photographically. So here's, and you'll notice there are a number of other things in the area. So let's think about what else we can do if we've got a telescope and we're observing. And a lot of these will apply to pretty much any size of telescope, I think. So let's start with the stars in the middle. Theta 1 Orionis, the trapezium. Can you see 4 or 3? Or are there more? And if you look in the double star catalogue, there are, I'm not sure what the actual count is, it's something like 8 stars, all attached or listed as part of Theta 1 Orionis, A, B, C, and so on. Next question to ask yourself when you're looking is, how far can you actually see the nebulosity spreading? It's, you know, if you've got on a nice dark night, it does actually go an awful long way. How far can you actually trace those arms, those sweeping arms out? Have a go. The one I keep pointing out, the big arc, almost swings all the way down to iota, to my eyes anyway. The other thing is to look for M43, Demiron's Nebula. Is that also visible? And I ask that question because I find I can't always see that. It's allegedly very bright, and you sort of think, well, there must be something wrong. But I think it's something to do with the conditions you're seeing it on a given night. And I certainly would not claim to be able to see M43 on all occasions that I'm looking at M42. Another interesting question, without any filters in, can you actually see any color? The received wisdom is that most deep sky objects, other than stars, you can't see any color. They're white because you're mostly seeing them with your rods, which don't detect color because they're faint. But Orion, the Orion Nebula is actually pretty bright. And so it's a reasonable question to ask. Can you detect any trace of color? Is it just white or is it something else? And certainly my experience of it is that without filters, on a really nice clear night, I often see it as slightly greenish, which kind of makes sense because it is bright in the green, as I'll explain when we talk about filters. But on particularly good nights, I also see just a trace here and there of brick red. Now, I may be kidding myself, but I do wonder whether I'm seeing a little bit of red light there as well. And the Orion Nebula, as you can see in most color photographic images, the predominant color is red. So why am I going on about green? Right. So let's talk about filters. So I've listed 3 particular filters there. And the reason you'd use a filter is partly to filter out light pollution, but they also increase contrast. So they should help improve what you see. So have a look without, then have a look with, have another look without. What's different? Can you see a difference? How do these things work? Well, they all work basically in the same way. So they have been designed. They're really quite high-tech devices, actually, in terms of their manufacture, to have really quite narrow parts of the spectrum between blue at one end and red at the other. And so they'll only pass parts of that color, that rainbow, parts of that color band. Let's start with O3 because that's the easiest. And so if you take an O3 filter, O3 is a particular wavelength of light that is emitted by oxygen that has lost. So an oxygen atom that's lost 2 electrons. And astronomers, for some reason, an atom that has all its electrons is 1. 1 electron lost is 2. 2 electrons lost is 3. I don't know, don't really quite understand because it doesn't really quite sort of add up the counting, but whatever. Anyway, oxygen 3 light is very much in the green. And it is, if you know your history, it's the light of planetary nebulae, and it's the light that Huggins picked up in his spectrum of the Cat's Eye Nebula and ended up being thought to be a new element, nebulium, and was it was much later worked out by Bowen that it's in fact oxygen light. But it's a nice bright green, and the point about green for visual observing is that green is the color that our eyes are most sensitive to. And Orion M42, like a lot of planetary nebulae and other nebulae, is actually quite bright in this O3 band. And so using an O3 filter, and similarly with the other filters, we'll talk about what they're doing in just a moment, that picks out the green, the light that you're most sensitive to, and so it leaves out the yellow, particularly of the street lights. And so it increases the contrast, and perhaps we can see more detail. But also that green means that if you're going to see any color in the Orion Nebula, it's going to be green. The red is potentially the light due to ionized hydrogen, so-called hydrogen alpha light, and predominantly M42 shines in the hydrogen alpha band. The problem with that is it's red light, and our eyes aren't terribly sensitive to it. But perhaps because there's so much of it there, just possibly my my impression of a little bit of brick red here and there is real. Don't know, but maybe. The UHC and CLS filters are different types of light pollution filter. The UHC's got narrow bands and the CLS rather wider. So basically, they're still blocking out the yellow, but they open up a bit on the in the green and the red regions. What I would urge you to do, whatever you do, is to make a record of what you see. Fine, you could just write some notes down, or you could do what I do, and I have a little voice recorder that I speak into, and then I type up the notes later. Or the other thing, so that's the equivalent of what Galileo did. Or you can make a sketch, like the Herschels, like Bond, and you can make it as simple or complicated as you like. And I'm going to shortly take a risk and show you some of my attempts. So that's the Orion Nebula itself. But I talked about fun, and I think part of the fun is to actually scan the wider area. So here's the local area around the nebula. I've scanned this from Sky Atlas 2000. So we've got the Orion Nebula here, M43, and we can follow that down to Iota, and there's a little bit of nebulosity there that you can sometimes see. But anyway, in most telescopes, you'll see that star as a nice triple. Going the other way, northwards, this is a favorite imaging target. This is the Running Man Nebula. Now, sometimes in the good conditions, I can see the nebulosity there. I'm being careful. I'm not telling you I can see the Running Man, because I can't, but I can see that there's nebulosity there. And then above this is NGC 1981, an open cluster, and that's nice and quite clear. If we're imaging, then of course around Alnitak, you've got the Flame Nebula over here, and then the big band of nebulosity with the famous Horseheads Nebula in that. Once or twice, and only once or twice, I've been able to see the Flame Nebula visually. And again, really, it's a detection only. But then you've got the belt stars. Delta Mintaka is a multiple, and Alnitak is also a multiple. Just below Alnitak here, Sigma, that's a fabulous multiple star. 5 or 6 you'll probably see there if you look carefully. But the whole of the belt area is actually an open cluster, Kalinda 70. You won't see that with a telescope. Step back, look with binoculars, scan that area with binoculars and see how many stars there are there. You'll be, if you don't already know it, you'll be surprised, pleasantly surprised, I hope. Okay, I promised to put my heart on a sleeve and show you my own sketches, so here we go. And they're not here as any examples of great artwork, but this is what we can do and get an impression. So this was something I did way back in 2003, and what I was trying to do here, so the stars have in fact been printed, and what I've been trying to do is to use that as effectively place markers to try and sketch out just exactly how much nebulosity I could see. So the stars are just guides. What we're recording is the nebulosity. So M43 is clear, And this was done with a 6-inch Newtonian. Somewhat naughtily, I haven't mentioned what lenses I used, but at the time I would have probably I'd have been using a 25mm and a 10mm Plössl, I would think. Later on, and that was from the northeast of England. This one also was done in from the northeast of England, where I used to live until 2010. And probably I did this up in the North Yorks Moors. So January 2010, so just before I left the area, actually, with a 12-inch Dob and a 15mm lens, no filter. And this is what I could see with a full moon, nearly full moon rising, which perhaps explains why I haven't managed to detect M43. Although, by all the maps, it should have been in the field of view. But here we have the trapezium. Here's the fish's mouth region. I've actually caught one of those bars, and I've got a big arc going out this way. Later on, actually, yes, 2015. This drawing I made when I was spending a month in the desert in Namibia. So I was using a 12-inch LX200, but it's a visual image, 25mm lens, so actually quite similar to this. And on this occasion, I can see Demarans Nebula. There it is. I'm not going to talk about astrophotography other than say, well, yes, you can. This is quite a nice one, I think, by one of my friends at Reading, Peter Tickner. And of course, there are many, many, many more. So here's M43. Here's the trapezium, and he's just managing to resolve some of the stars there. That is clearly the fish's mouth region, and that's that big arc that I keep going on about. Okay, let's move on to the final segment of my talk and think about, well, what is M42? And we need to use a really deep image. So here's a really deep image, and take ourselves back into context. So here's the whole constellation. Here's Betelgeuse, Rigel, Bellatrix, safe. Get it right this time. Here's the belt. There, I think I can just see a little black dot, which I think is probably the Horse Head. Here's the Flame Nebula, and here's M43, the Running Man, and NGC 1981 up here. You can see the star cluster I talked about, but you can see that the Orion Nebula, you can now see in context as part of a much, much bigger complex of molecular clouds. And we now know it's just under 1,400 light years away from us. And this region is a star formation region. So what's going on here is we've got lots of hydrogen. There's quite a lot of dust in there, so there's other elements present too. And gradually, parts of those clouds are collapsing to form new stars. And that is particularly active around M42 itself. And I found this image, which explains it quite nicely. So from our point of view, we're over here on the left, looking to the right. And so we're actually looking through some older open stars in open clusters, gradually getting denser, and then a new cluster forming really around Theta 1 Orionis, and behind it, the molecular cloud continues. So what's happening is, in effect, the star formation process is burning backwards away from us into the molecular cloud. And in the regions which we can't see, because the stars are too deep into the cloud, and so can only be seen by the professional astronomers with infrared, we've got lots of forming stars. But these things have been detected. Here, we've got effectively Theta 1 Orionis. And what we've got there is some massive stars, much, much larger, higher mass than our own sun. And because they're much larger, they have to keep their integrity, they have to throw out a lot more energy. And that makes them really very, very hot indeed. And because they're so very hot, they go out beyond red hot, orange hot, white hot. They actually, if you like, become so blue hot that they're actually emitting most strongly in the ultraviolet. And it's the ultraviolet light hitting the remaining gas, ionizing it, and providing the energy that actually makes the whole nebula glow, particularly with the light of hydrogen, but also the other elements that are there, so the oxygen as well. And really, it's the same process that we see on Earth in neon lights, except instead of using electrical discharge, we're using ultraviolet light to make the gas glow. But that's what we're seeing. That's what's making the gas glow. The other thing that is happening is because those stars are so large, hot, they're also quite violent in environments, and they're actually throwing gas, pushing gas out. Partly it's radiation pressure, but it's also the stellar wind, the equivalent of the solar wind, and it's strong enough that it actually pushes the gas around. And so over at the back here, it's actually pushing the thicker cloud, which hasn't yet formed into star, compressing it. And it's that compression, the shock waves in this region here, that actually then start off the process of collapse to make a new generation of stars, which astronomers have detected here. And with time, that will move back and back through that molecular cloud. We know there are new stars there because we can detect objects like this, things called Herbig-Haro objects. So in the murk here, you can just see a glow, is a new star. And as it collapses, it picks up angular momentum. And it can only spin so fast because that's what angular momentum makes it do, like an ice skater pulling her arms in. And so it's got to get rid of that angular momentum. And the way young stars do that is they actually throw it out at right angles, basically at the poles. And you get these jets, which we can detect with each of these bright blobs is actually a shock wave. Effectively, it's a sonic boom. And so what we've got is a great jet of gas blowing out from the new star here, taking away the excess angular momentum. Because if it doesn't do that, it'll then become unstable. It'll then flatten out into a disk, and it'll actually, in the extreme case, will actually spin itself into pieces, literally. And there will actually be, out of the other pole, a companion jet going in the opposite direction. And in some images, I picked this one because it was nice and clear, but in some images, you can actually see the two jets from the same star. I've talked about disks. Also in Orion, we can see disks, planetary systems in formation. So here are a catalogue of pictures that are picked. I think most of these were probably done with the HST. And you can see these little dark disks. You can just, some of them you can see the jets coming out the top and the bottom. Some you can see the star in the middle. Some star is actually hidden by all the dust. But there's an incredible variety of these. And what you're seeing here is the beginnings of the conditions that will allow planet formation around these brand new stars. That I thought I'd hidden. So I've come to the end, and I've given you a short little history of observations of M42, and I've tried to look at different cultures as well as the technological range. So from naked eye through telescopic sketches, ultimately through to imaging. Haven't touched on spectroscopy and things like that, of course. Then, I hope, giving you some ideas, some interesting challenges, things you can do the next time you go out and have a look at the M42 and its surrounding constellation. And we've also had a little look at what M42 actually is and what it means and how it helps our understanding of how stars form and develop, and of course also develop planetary systems. So with that, I will stop and happily take any questions.